Welcome to session 1 of the model 3 in the subject applied hydraulics. Applied hydraulics. So the code of the subject is 18CV43. 18CV43. Okay. In this session, in this model, usually we are deals with the non-uniform flow. In the model 2, we are discussing related to the uniform flow only. Under that, we are discussing mechanical section and specific energy curve and all these things. Once you are familiar with the specific energy curve, mechanical section, and all these things, next we pass on to the what about the non-uniform flow. So uniform flow is defined as one in which for a given length of channel, depth of flow, slope, discharge, and all these things are constant. Then such type of flow is called as uniform. The non-uniform flow is one in which the hydraulic parameters are not constant for a given length of a channel. Such a type of flow is termed as a non-uniform. Type of flow is termed as a non-uniform flow. Under this model, we are discussing about the hydraulic jump, what about the relationship between the sequence depths, Raoult's number, and loss of energy, how to find out and probably related to the particular one, and then coming to the gradually varied flow. Under that, we are studied about what are the equations for gradually varied flow, as well as what about the loss of head and all these things, and also what are the different types of the profiles in a gradually varied. So before we pass on to the actual non-uniform flow, just I am briefing about the specific energy and all these things. Specific energy is defined as it is the energy per unit weight. Per unit weight of water. Usually it is denoted as E, capital E, equals Y plus V squared by 2G. Okay, if you draw the specific energy curve, then it is usually parabolic in nature usually, but other than minimum specific energy, if you go anywhere, you are getting a two depths of flow. That particular flow depth of flow is usually termed as a conflict depths, Y1 and Y2. So at minimum specific energy, the depth of flow is called as Y minimum or Y critical, and also it is termed as critical specific energy EC, and corresponding depth is termed as YC, critical depth of flow. And also some of the formulas are using to find out the value of YC. Usually YC can be calculated by YC cube equals Q square by GB square. YC cube equals Q square by GB square, where Q is the discharge, B is the width of the channel. Usually it is rectangular in nature. There is an equation for rectangle one, and also the critical specific energy for rectangular section equals 1 point times the critical depth of flow. And also we are well versed with the what about the Raoult's number. That is Raoult's number. It is basically used to classification of the type of the flow, whether it is supercritical flow, subcritical flow, critical flow, depending upon the value of F. F equals 1, then it is critical. If it is less than 1, subcritical, and if it is greater than 1, it is supercritical flow. So usually F equals V by root Gy, where V is velocity of flow, G is acceleration to gravity, and Y is depth of flow. These formulas are commonly used when we go for deriving or getting an equation of specific energy and all these things. And the same thing is utilized in our derivations related to the hydraulic jump and all these things. Unless otherwise you are familiar with the specific energy, what is specific energy, what is the relationship between specific energy, depth of flow, and all the critical depth of flow, and all these things, then it is somewhat difficult to understand them. So once you are familiar with what is specific energy, what is YC, what is EC, YC stands for critical depth of flow, EC stands for critical specific energy. Other than EC, other than YC, if you go for anywhere, you are getting two depth of flow as well as two specific energy. So once you are familiar with the what is specific energy as well as what about uniform flow, non-uniform flow, and all these things. Okay, next we pass on to the next one. Slide is non-uniform flow is the flow for which the depth of flow is varied with respect to the length. Varied with respect to the length. This varied flow can be either gradually varied flow or rapidly varied. It is depending upon the situation. If the variation of the flow is for a long length or length of the channel is more than such a type of variation is called as gradually varied flow. If the variation of flow occurs for a short length, then such a type of flow is called as rapidly varied flow. Okay. Usually gradually varied flow occurs on the upstream side of the dam or a reservoir. Here in the upstream side of the reservoir, the depth of flow is goes on varying along the length of the storage capacity or along the back side of the or upstream side of the dam. And rapidly varied flow is occurs just below the spillway or weirs or crustate and all these things, where the depth of flow is abruptly changed for a short length or short distance. So once you are familiar with the gradually varied flow and rapidly varied flow, then where exactly it is occurs? Usually the control structures are used in the channel. Then that means if you go for obstruction for the flow, then the gradually varied flow or rapidly varied flow may occurs. When any obstruction is found in channel, just like dam, reservoir, crest gate, or weirs, spillways, and all these things. When a sharp change in the channel slope takes place, there is a sudden change in the slope of the channel, then also there is a gradually varied flow or rapidly varied flow. So under non-uniform flow, very first thing is we are discussing about the hydraulic jump or standing brake. Hydraulic jump or standing brake. So what is hydraulic jump? At the downstream side of the dam, the height or depth of water increase rapidly over a short length of the channel. That's what is called as rapidly varied flow. Hydraulic jump is formed when the rapidly varying flow occurs at the downstream side of the reservoir. This is because initially the flow is shooting flow at the depth of water less than the critical depth, and it is an unsuitable type of flow and does not continue to the downstream side. Means if the hydraulic jump occurs, means before hydraulic jump depth is y1, after hydraulic jump depth is y2. So usually the y1 is less than yc, where yc stands for the critical depth of flow, where the critical specific energy occurs. Critical specific energy is occurs. Okay, so usually y1 is always less than yc, as well as y2 is greater than yc, then only hydraulic jump is occurs. Then this is shooting will convert itself into streaming. The flow and depth of water will increase. Means at the once hydraulic jump occurs, automatically depth of flow is increases. Means y2 is always greater than y1. y2 is always greater than y1. The sudden increase of depth of water is called hydraulic jump or standing. Hydraulic jump or standing. So sudden increase in the depth of flow is usually termed as hydraulic jump or standing. The rise of water level, which takes place due to the transformation of unsuitable shooting flow, it is called as supercritical flow. Usually supercritical flow is found out by using the Proud's number F equals V by root Gy, where V is velocity of flow, G is acceleration, and Y is depth of flow. Means shooting to the stable streaming flow means subcritical flow. So the hydraulic jump is occurs only when the flow changes from supercritical flow to the subcritical flow. Means supercritical flow means before hydraulic jump the value of Froude number is greater than 1. Subcritical means after hydraulic jump the value of F is less than 1. F is mainly depending upon the V as well as Y. Where V is velocity of flow, Y is depth of. So if the flow changes from supercritical to subcritical flow, then only the hydraulic jump occurs. When you go for solving the problem related to the hydraulic jump, first you decide whether the hydraulic jump occurs or not on the basis of the Froude number, and you calculate the value of Froude number, which is F1 is before hydraulic jump Froude number, F2 usually after hydraulic jump. Find out the value of F1 and F2 on the basis of that to decide whether hydraulic jump is occurs or not. The hydraulic jump is also called a standing wave because it is standing at a place for a few seconds or minutes. Once the hydraulic jump occurs at that particular place, it is stationary for a few seconds. That's why it is called as a standing wave. So places of occurrence, where exactly the hydraulic jump occurs. If you observe the figure, at the foot of the overflow spillway dam, spillways are hydraulic structures usually constructed to allow the excess of water to reach the downstream side from the dam. So there is excess of flood occurs in the dam, and automatically they allow the water to reach the downstream side by through the spillways. So at the downstream of the spillway, hydraulic jump occurs. Behind a dam of steep slope, so the dam having a steep slope, then also hydraulic jump occurs at the particular place. Below the regulating sluice, usually sluice gates or gates which are provided above the crest of the spillway or weirs to increase the storage capacity. If there is excess of water is entering into the dam, automatically they raise the sluice gates. Then automatically water is reached the downstream side in between crest of the weir as well as bottom of the sluice gate. Once water reaches downstream side, automatically hydraulic jump occurs. When a steep slope channel suddenly turns to flat, there is a sudden change in the slope of the channel, then also hydraulic jump is occurs. Uses of hydraulic jump. There are so many uses which are related to the hydraulic jump that are related to the civil engineering field. So some of the applications or uses of the hydraulic jump are: it is used as a to dissipate excessive energy. And also it is called as energy dissipator. Some amount of energy is lost. Usually it is termed as HL, loss of HE, loss of energy. Once the hydraulic jump occurs, automatically some amount of the energy loss is occurred. That's why it is also termed as energy dissipator. So to dissipate excessive energy, if the energy is too high, then if you want to reduce the energy, then we are creating a hydraulic jump. By that, some amount of energy loss will take place. To increase the water level on the downstream side, if you want to increase the water level on the downstream side of the any section, channel section, then we are creating a hydraulic jump. Automatically, the depth of the downstream side is increased because y2 is always greater than y1. Then only hydraulic jump occurs. To reduce the net uplift force by increasing the weight, that is due to increased depth. If you want to increase the depth, then also you are using hydraulic jump. To increase the discharge from sluice gate by increasing the effective head causing flow, means just below the crest gate, the hydraulic jump, because usually crest gate are introduced to increase the storage capacity of the reservoir or dam and all these things. To provide a control section, if you want to control the sections at any place, then also hydraulic jump may occur. For thorough mixing of chemicals in water, if you observe in some of the water treatment plant, they are adding the chemicals for treating the water. For example, alum is commonly used for treating the water. So here the effectiveness of the alum or any chemicals which are added to the water is mainly depending upon the how we are mixing the chemicals with the water or agitation speed and all these things. Mixing is good, then automatically the removal efficiency of any solids or colloids or any contamination present in the water is more. If they are not mixing thoroughly, then the effectiveness is decreased. To increase the effectiveness of the chemicals, they are utilizing the hydraulic jump. So once hydraulic jump occurs, automatically turbulence, eddy turbulence will be created. By that, the mixing will take place to the maximum extent. For aeration of drinking water, aeration is process in which just you bring the water to mix it to the atmosphere. To the atmosphere. By that, it is possible to remove some of the uh, contaminants which are present in the water. For removing air pockets in a pipeline, if there is any air pockets are present in the pipeline, then by using the hydraulic jump, it is possible to reduce or remove the air pockets present in the types of hydraulic jump. Based on the initial Froude number F1, hydraulic jumps can be classified as follows. Angular jump. Such jump occurs when the initial Froude number 1 means before hydraulic jump is between 1 and 7. In such a jump, there will be surface undulations due to low level turbulence. It would result in insignificant energy loss. Means if the value of F is 1 to 1.7, then the hydrogen occurs. The particular jump is termed as an angular jump. Weak jump means if the value of F1 between 1.7 to 2.5, then it is weak jump. The head loss is low, air loss of head will be less. In this type jump, series of small rollers form on the surface and the loss of energy due to this type is small. Here, some amount of energy will be lost since some small rollers of the turbulence is generated in the particular case. Oscillating jump. It occurs if the F1 is between 2.5 and 4.5. So usually this classification made on the basis of the F1 value 1. In this type of surface will be wave jets. If the water shoot from the floor to surface, jump moves back and forth causing some damage. Such jump should be avoided because means if such a type of jump occurs, it may damage the structure, the bottom itself. So try to avoid this one. Steady jump. If the value of F1 between 4.5 to 9, then such a type of jump is called as steady jump. Requires still basin to confine jump. Means if the F1 value is more than 4.5 to 9, then we are providing the still basin at the bottom of the spillway and all this thing to avoid the chance of erosion as well as energy dissipation and all these things. Here, energy dissipation is up to 45 to 70%. Strong jump. It occurs when F1 is more than 9. It will be rough and violent. Huge rollers are formed in the flow. Energy dissipation will be very high and is also up to 65%. These classifications are made on the basis of F1 as well as what about the amount of energy dissipated on these things. So this figure gives the relationship between the specific energy curve as well as the hydraulic jump. If you observe the specific energy curve, C stands for critical specific energy. Critical specific energy is one where depth of flow is critical. Usually in the right hand side it is DC, otherwise YC. This is critical depth of flow. So if you observe the middle one, okay, what surface D1, depth of flow before hydraulic jump is D1 and velocity is V1. Where D1 is the point depth of flow, it is less than the DC or critical depth of flow, and it is before hydraulic jump. Okay, after hydraulic jump, velocity is V2 as well as depth of flow is D2. D2 stands for depth of flow after jump. Then automatically, if you observe in specific energy, specific force curve, then D2 is greater than DC. D2 is greater than DC. And also some amount of energy loss delta E will be occurs. That's what is called as energy dissipator. So in very simple word, hydraulic jump occurs when the flow changes from supercritical to subcritical flow. One condition. Another one means initial F1 is greater than 1, F2 is more or less than 1. And also hydraulic jump occurs. There are two jumps before hydraulic jump and after hydraulic jump. Usually this termed as a sequent depths. Sequent depths. Y1 is before jump, Y2 is after jump. Where Y1 is always less than critical depth, YC or DC, and Y2 is depth after jump, it is always greater than critical depth or DC. Then only the head or jump occurs. So if you are decided on the basis of the data given in the solving the problem, so we decide whether head or jump occurs or not on the basis of the Proust number as well as value of Y1, Y2, YC and all these things. Analysis of hydraulic jump. The equation of hydraulic jump can be derived making the following assumptions. The channel bed is horizontal so that the component of the body of the water weighing in the direction of flow can be neglected. Since it is channel bed is horizontal, we are neglecting the water weight along this direction of flow. The frictional resistance channel is small length over which jump occurs is neglected. Since the length of hydraulic jump occurs is too less, that's what is called as rapidly varying flow. Therefore, we are not taken into consideration of the frictional resistance. The channel is rectangular in section, so it is applicable to the rectangular channel. The portion of the channel in which hydraulic jump occurs is taken as control volume. It is assumed that just before and just after the control volume, the flow is uniform and pressure distribution is hydrostatic. Means since we are considered the section of the channel is same throughout the section, therefore there is a control flow of volume is occurs when the hydraulic jump will be generated at any place or created at any place. So next we pass on to the derivations. This one is very important. Derivations usually in the examination they may ask the question like that: derive an equation. Show that derive equation for the hydraulic jump in the rectangle channel, or they may ask what about the relationship between the sequent depths and all these things. Sequent depth is the depth which occurs in hydraulic jump, means Y1 before jump, Y2 after jump. So we are supposed to show the relationship between Y1 and Y2 when the hydraulic jump is occurs. If you are see the figure, so here the Y1 is the depth of flow before jump, Y2 is depth of flow after the jump, A1 is the cross-sectional area of section 1-1 or before jump, A2 cross-sectional area after jump, V1 velocity of flow at section 1, V2 velocity of flow at section 2, F1 is the hydrostatic pressure which is acting at section 1, and F2 is also hydrostatic pressure acting at particular section 2. Okay. So net force is F1 minus F2, otherwise difference between F1 and F2 is the net force acting on the particular. Consider in hydraulic jump or in a prismatic channel. Prismatic channel means it is having uniform cross-section area. The channel is having uniform cross-section area. Floor carrying a discharge tube as shown in figure, that the depth of flow before jump section is Y1, depth of flow after the jump section is Y2. Consider the hydraulic jump occurring between two sections 1-1 and 2-2 as shown. The forces acting on the control volume are hydrostatic pressure force F1 and F2 acting in the opposite directions. Component of weight W sin theta in the direction of flow, where we are treated as neglected. Shear stress or frictional resistance acting on the contact area. Frictional resistance acting on the contact area. From the impulse momentum equation, algebraic sum of the forces acting equals change in momentum on the control volume. It is Newton's second law. On the basis of that, as algebraic sum of the forces acting equals change in momentum on the control volume. So consider left hand side first. Okay, from the equation 1. So then forces F equals F1 F2 plus W sin theta. As per the assumptions made above, slope of the channel is too small, therefore sin theta is equals to 0. Hence we can neglect the particular term. The total forces acting is difference between F1 and F2. But F1 and F2 being electrostatic pressure, we have F1 equals gamma into A1Y1 and F2 equals gamma into Y2. Otherwise, sigma force can be written as the difference between those two, where A1 A2 are the cross-sectional area before and after jump. Y1 Y2 are the centroidal depths. F1 and F2 means from the respective liquid surface. Usually, these Y1 and Y2 can be written as Y1 by 2 and Y2 by 2, or half of the depth of the rectangular section. It is acting as the centroid of the rectangular section. Consider the right hand side. This change in momentum equals momentum before the jump per unit time or momentum after the jump. So momentum before the jump can be written as mass by time into change in the velocity, v1 minus v2 or v2 minus v1. Okay, so mass by time into change in velocity. So length into L into volume by time into v1 minus v2. So volume by time can be written as discharge. So L into discharge into v1 minus v2. So L into Q. Okay, v1 can be written as Q by A. Q equals AV. Therefore, V can be written as Q by A. So v1 can be written as Q by A1 and v2 can be written as Q by A2. So you bring Q outside, then L into Q square into 1 by A1 and minus 1 by A2. Change in momentum per unit time can be written as gamma by G into Q square. This one is for total length, this one is for unit time. Then it is gamma by G into Q square into 1 minus A1 minus 1 minus A2. So substituting equation A and B in equation 1. So equating those two, then gamma into A1 Y1 y minus gamma A2 into Y equals gamma by G into Q square into 1 minus A1 minus A2. Rewriting this equation, this can be written as A1 Y1 plus Q by G A1 equals A2 Y2 plus Q2 by G A2. This is the general equation for hydraulic jump in any type of the channel, whether it is rectangular channel or any channel. Usually A1 Y1 plus Q2 Q square by G A1 equals A2 Y2 plus Q square by A G A2. But when you go for rectangular section, cross section of the rectangle can be written as V into Y, width into depth of flow, bottom width into depth of flow. It is also V into Y2. It is depending upon the Y1 and Y2 value. So, and Y can be written as where exactly hydrostatic pressure acting at the centroid. Centroid is Y1 by 2, Y2 is also Y2 by 2, and small q stands for unit discharge. Small q stands for unit discharge. So big capital Q stands for the discharge in a whole section, but small q is discharge for unit width. Usually this can be done as capital Q by B. Capital Q by B, which gives the discharge per unit width. Unit width is for one width. What about the discharge? Substituting all these values in the equation 2. Okay, so you substituting the values y1 by1 into y1 by 2 plus q square by gb square y1 equals, and finally we get the equation. Okay, 2q square by g equals y1 y2 into y1 plus y2 is equation 3 after simplification. And all these things. Equation 3 is the general equation of hydraulic jump in a rectangular channel. It can be written as, so if you are further simplify, it can be written as y1 square y2 plus y1 y2 square minus 2q square by g equals 0. So this is the general equation for hydraulic jump in a rectangular section. Usually in the examination they may ask for the what is the relationship between the sequent depth or hydraulic jump, before jump and after jump and all these things. Then we derive up to this point. Okay. In next session, we will continue this particular one and get the relationship between the Proud's number as well as sequence depth and all these things. Thank you.